Now let's look at how we can calculate the pH after we've added 10 milliliters of sodium hydroxide. So the first thing we need to do is to again imagine what we have in our beaker. And so at this point, we have added sodium hydroxide, which has reacted with the HA to form some A minus. And so we have both HA and A minus in our beaker. And so we have a choice of two different equilibrium reactions that we could use to calculate the pH. We have HA in our beaker, which will react with the water to form conjugate base and H3O+. But we also have a significant amount of conjugate base, which will react with the water to form HA and sodium hydroxide. Since we have a significant amount of both HA and A minus in our beaker, we can choose which of these two reactions we prefer to use to solve for the pH after the addition of 10 milliliters of sodium hydroxide. So I'm going to choose the base hydrolysis for the following reason. I'm adding OH minus, and this equation contains OH minus, and so there's going to be a place for me to put the initial amount of OH minus that I have in my beaker after the addition of 10 milliliters. And I am going to know something about how much HA was in my beaker from my previous problem, and so I'm going to be able to have a place in my ice chart to put both of these initial concentrations. So if I have a choice of reactions, I'm going to choose the one that has the species which I've added to my beaker. So we're going to start with the equation, the equilibrium reaction between conjugate base A minus and water to form the conjugate acid plus OH minus. Now initially in my beaker I have put some HA, and in fact I know that I have put 0.00245 moles of HA. So from the previous problem, we know that 0.5 grams of HA is 0.00245 moles of HA. I am going to need to know how much OH minus I put into my beaker. So what's the initial amount of OH minus I put in my beaker? And so I'm going to need to know something about the number of moles of OH minus that I put in my beaker. And I have the concentration of sodium hydroxide that I'm using, and I have the volume. And so I should be able to calculate the number of moles of OH minus from the concentration times the volume. And so I have 0.100 molar OH minus, and I've added 0.010 liters because 10 milliliters is 0.01 liters. And so the number of moles of OH minus that I've added to my beaker is 0.001 moles of OH minus. Now, I need to be careful because I need to think about what is the total volume that these moles are now in. So I started with 75 milliliters of the solution of HA, but I have added 10 milliliters to that. So my total volume is now 85 milliliters. So the volume that these moles are in is equal to 85 milliliters or 0.085 liters. And so to calculate the concentration of my HA and my OH minus that are currently in this beaker, I need to know how many moles are in what total volume. And so I can calculate the concentration of HA as 0.00245 moles in 0.085 liters, and the amount of the concentration of OH minus to begin with is 0.001 moles in 0.085 liters. And so my initial concentrations of HA and of OH minus are 0.0288 and 0.0118 molar. Initially, I have not put any conjugate base into my beaker. So remember what I personally put into the beaker was 0.5 grams of KHP, 10 milliliters of 0.1 molar sodium hydroxide, and 75 milliliters of water. That's what I'm going to use for my initial conditions. Now, if I think about this problem, I know that my Kb value, because this is a base hydrolysis, I'm going to need a Kb value for solving this equilibrium reaction. Since the Ka value is small, my Kb value is going to be small. And so that means that I should have very few products at equilibrium. And right now, I'm starting with all products and no reactants. And so I'm in that situation where I'm not going to be able to ignore X unless I do a limiting reagent problem first to form reactants and then come to equilibrium from the reactant side because I have a small K. So let's start by calculating our K value for this reaction. Remember that Ka times Kb has to equal Kw, and Kw is 10 to the minus 14. And so I know my Ka. My Ka is equal to 3.9 times 10 to the minus 6. And I want to find Kb, and I know 3.9 times 10 to the minus 6 times Kb is equal to 10 to the minus 14. So I divide both sides by 3.9 times 10 to the minus 6, and I get a Kb value of 2.6 times 10 to the minus 9. And so in fact, Kb is quite small. So I'm going to need to do a limiting reagent problem to make as many reactants as I can out of the amount of products that I'm starting with. Luckily, this is a nice simple 1-to-1-to-1 reaction, and so I can see that since the OH minus is the smallest concentration, it's going to be my limiting reagent. And so I'm going to use it all up, and when I use it all up, I use up 0.0118 of my weak acid. So I use up this amount of my weak acid. So if I subtract this amount, because that's what I used up, from this, I will get the amount of HA that I have left. And so I have 0.017 molar of the HA. And when I do that, I'm going to make some A minus. And every time I use up 0.0118 of the OH minus, I'm going to make that amount of conjugate base, A minus. So I'm going to have 0.0118 of the conjugate base. And so those are my new initial conditions. And now I can see that when I get to equilibrium, so when I go to equilibrium in order to make some OH minus, X will represent the amount of OH minus that I've made, and X will be small because Kb is small. And if X is small, I can ignore it relative to this concentration and this concentration. So my change to get to equilibrium is to make X of this, make X of this, and lose X of this. And so at equilibrium, because I'm going to be able to ignore X relative to this and X relative to this, I can write that I should have 0.0118 of the conjugate base, 0.017 of the conjugate acid, and X OH minus. So my Kb value is equal to my product concentrations, X times 0.017, divided by my reactant concentrations, 0.0118. And so if I solve for x, I will find that x, which is equal to the OH minus concentration, is equal to 1.8 times 10 to the minus 9 molar. And so from that value, I can get the POH by taking the negative log. And so if I take the negative log of that number, my POH is 8.75. Finally, I can find the pH by remembering that pH plus POH is 14. And so 14 minus 8.75 will give me my pH, and my pH is 5.25. So after the addition of 10 milliliters of sodium hydroxide, we have a pH of 5.25, which is what we would expect. The pH has increased from the initial pH of 3.45 because I've added base to my solution.